For this course, you formally register for this course?
Yes, sir.
Okay. Next. University of Balochistan.
Assalamu alaikum, sir.
Wa alaikum assalam wa rahmatullah.
Sir, I'm Muhammad Asghar. I'm a field student from University of Balochistan.
Good.
Assalamu alaikum, sir. My name is Saima and I am a field student from Balochistan.
Thank you so much. Karachi University. Karachi University, sir?
University of Gomal University, Delhi.
Aage. Okay, so again, Assalamu alaikum wa rahmatullahi wa barakatuh. We would resume, as always, by summarizing what we have discussed yesterday. And yesterday, I tried to explain spin echo experiment. I emphasize the need of certain techniques, giving the example of a fully coupled C13 NMR spectrum. And then we discussed that the content of information in fully coupled C13 NMR spectrum is tremendous. There are lots of coupling, direct couplings, one bond couplings जिनको कहते हैं, or long range coupling which is 1-3, 1-4 couplings. So there are plenty of different types of couplings. The knowledge content is very, very high, but interpretation is a major problem. We keep emphasizing on the need that there is a need of an experiment which provides you information about carbons, about the chemical shifts of carbon and the multiplicity of carbon. Across the board, we also kept discussing the sensitivity issue which is related to C13 more than any other nucleus. And then we moved into the history and start discussing different options when people had fully coupled C13 NMR spectrum and when they were not able to interpret the results. The first thing which they have done, they wanted to remove the long, and they have done an experiment called off-resonance decoupling, bringing a radio frequency oscillator, tuning the radio frequency oscillator on long-range coupling frequencies, and then removing all long-range couplings. We learned that even that was not so useful, because even for a simpler molecule like alpha-pinene, which we have discussed yesterday, the complexity of coupled C13 NMR spectrum is fairly serious, and it becomes extremely serious if a larger molecule. So even for alpha-pinene, interpretation is not that easy, though we tried yesterday and we were very happy to interpret some of the results. What we have also learned was that if we have a molecule like cholesterol, which is a very small molecule as compared to the world of macromolecules, when you have lots of proteins in the world, thousands and thousands of proteins, when you have lots of other biopolymers like chitosins and saccharides and cellulases and starch and whole range of different types of biopolymers, even the cholesterol is not so easy to interpret, and it is almost close to impossible to interpret the results of a fully coupled C13 NMR spectrum. And then we went into the history again and said that this was the problem, and people said even in the absence of a long-range coupling, this direct one-bond coupling between proton and carbon is itself a problem, so we would go for a broadband decoupling. Remember, decoupling is a process in which you remove one or several protons from the system so the coupling doesn't appear. And it can be a double resonance experiment, which I told you yesterday. It's a very easy experiment, spin decoupling, giving the example of ethanol, that if you decouple CH2, if you resonate CH2 with a constant radio frequency oscillation, this methyl will appear as a singlet, and it is a selective decoupling, homonuclear in nature, because proton is decoupled selectively. It's called selective decoupling. And then I talked to you about broadband decoupling, and broadband decoupling was the easiest experiment, though the consequences were not very useful. The experiment was so easy that you bring a radio frequency oscillator and you tune the frequency of your oscillator to the whole band of protons, chemical shift band of proton, and when you oscillate all the time, constantly turning on the radio frequency oscillator on the frequency of proton, your carbon would not see any proton. And when it would not see any proton, it would appear as singlets. Your problem was partly solved because you were able to confirm how many carbons you have. You were also able to know what is the chemical shift of chemical shifts of your carbons. Remember, overlapping in carbon-13 is fairly rare because the width of the carbon-13 spectrum is fairly large, from 0 to 220 and even to 240. So you have a very large spectral width, 0 to 220 or more, so overlapping is fairly rare. Even slight difference in electronic environment will make carbon appear at a different position. On the other hand, proton has a spectral width of 0 to 10 or 12, and every compound on the face of the earth, million, trillion or zillion, they all appear between that. Whether a protein or a small ethyl alcohol molecule, everything appears between 0 to 12. So chances of overlapping is extremely high in proton NMR spectrum. Now, if I tell you that I like proton NMR spectrum because it is sensitive, and small quantity will give you full spectrum because all hydrogens are NMR active, you would agree with me. But if I tell you that I don't like proton NMR spectrum because it is not selective and it has a problem of overlapping, so you would agree with me also. On the other hand, the opposite for carbon-13, that it is insensitive by virtue of the abundance and by virtue of magnetic susceptibility, so-called gyromagnetic ratio. I don't like it, but I like it because it is more selective. You have the choice of selection of carbons because there is no overlapping, rarely overlapping. Of course, you would see overlapping in very large molecule, you would see overlapping, but chances of overlapping in a broad carbon spectrum is several fold less than the overlapping in proton NMR spectrum. And remember, these two properties, that proton being sensitive and carbon-13 being selective, is being used to the maximum in the development of NMR spectroscopy. is so wonderful that people have taken the advantage of the strength of a technique, putting them together and develop new techniques, right? But at the end, we were so worried that, of course, it is a fact that we get a one carbon peak for each carbon, and overlapping is fairly rare. Chemical shift is quite clear. There is a problem that we miss out a very important information, which is about the multiplicity. You can appreciate the importance of multiplicity when you make the structure. When you deduce the structure, when you determine the structure of an unknown compound, then it is a very important piece of information. Very important piece of information, that which methyl is what, or which carbon is what, with a methyl or a methylene or methine or quaternary carbon or whatever. So, though a problem of overlapping was solved, but a very important piece of information was missing, and then we said that somebody brought forward, solved the problem by using an attached proton test, and this attached proton test, they were able to modulate different types of carbons on the basis of their proton, and you see two sets of carbon, one appearing on the one face and the other appearing on the other face. And that's how you partly solve the problem of multiplicity assignment. I told you that there are 4 sets of carbons, but here you can recognize 2 or maximum 3 by virtue of the fact that quaternary carbon is always a very small peak, right? So it was the attached proton test. And I showed you this last slide also, in which I showed you that you can see that some of the peaks are appearing in the negative phase, and some of the peaks are appearing on the positive phase also. And if I tell you that I can absolutely reverse it by placing my detector on the other end of the Y, you should not really be worried about that also. The CH3s and CHs which are appearing in the negative phase can appear on the positive phase if I just place the detector on the other side. So see, the placement of a detector has lots of bearing. So you can have these 2 sets of carbon, either plus or minus, depending on the position of the detector. Okay? Is all right? So it's just a choice of angle where you want to turn on your detector also. One thing which I want to make clear in response to what Sarosh asked several days ago when she was worried about the price of probe, as if it is going to be her wedding gift. I told you that the probe is the most expensive part of an NMR spectrometer other than the magnet, because of multiple reasons. And probe, the reasons are that you have detectors all over, radio frequency oscillators all over, not one but several of them. And you have, on the other hand, thermal coils to heat the samples, and you have cryocoils to cool the samples, and then you have so many of them, so you have tremendous capacity in this small probe, which is a cylinder-like thing, and therefore it is expensive piece of equipment. On the other hand, the choice of a probe is a very crucial choice. If you're an organic chemist and if you want to work on proton and carbon, the precision is that you should really buy a proton carbon probe. Reason is that you would like to have a precision of radio frequency oscillation to an extremely high level for proton and carbon. if you are an inorganic chemist who are working on multiple of different nuclei, then you go for a multi-nuclear probes, which has so many of radio frequency oscillators, each capable of giving different types of radio frequency for a whole range of different. If you are a protein chemist, you would like to work on a triple resonance probe, because a protein chemist have interest in carbon, hydrogen and nitrogen. The oxygen they deduce by themselves, they are not so worried about it. So they get a triple resonance probe. Single resonance probe, proton probe. Double resonance, proton carbon. Triple resonance, proton carbon nitrogen. And they are called TXI probe. TXI probe. TXI probe. I don't know why it's called TXI probe. Honestly, I don't know. But when it is cryo-cooled, it's called TCI probe. And I don't know either why it's called TCI probe. Cryo-cooled triple resonance probes also. So this was the choice of a probe which I want to tell you. Going back to the discussion, remember I told you that the collapse of quartet, triplets and doublets gives you a singlet, gives you singlets, and these singlets are relatively easier to interpret and they have a large intensity which you expect from a triplet. When triplet will collapse into a singlet, it will be increased in size also. When a quartet will collapse into, ये तो समझ में आने वाली चीज है ना? So when a doublet will collapse into singlet, you would have two doublets mixed together, one intensity also. What people have observed was that the intensity enhancement was several fold more than what we expect from a normal collapse of a multiplet into a singlet also. And it took people a decade to explain why it actually happened. In between, there were lots of clever minds were working on lots of different types of techniques independent of hardware. You see, hardware was the first choice of NMR spectroscopist when the NMR spectroscopy developed as a field. Built large magnets. Permanent magnets are not suitable of building large magnets, so let's go to the electromagnets. Electromagnets are good enough for a certain level of magnetism. If you want to build a much larger one, then you go to a superconducting magnets. And the superconducting has no limits. The sky is the limit. You can go to every level of magnetism. The constant is that the technique would become something else, because you are dealing with the radio frequency until the precision frequency, radio frequency, it is an NMR spectrometer. And if precision frequencies goes to some other level, then it becomes something different, which nobody wants to have, So, sky is the limit. This was and people were developing cryoprobes, people were developing probes in which sensitivity increases a gaseous helium. So when gaseous heliums are introduced into the electronics of the probe, then they cool down and you have a less of resistance, more of a conductance, the signals the noise is reduced, sensitivity increased. They were all hardware dependent things, right? Of course, shimming is also hardware dependent thing when you try to homogenize your magnetic field, and there were number. But remember, there were lots of clever minds who said, can't we do it without improving the hardware? Can we do something with this spin? And the first and foremost technique was pulse Fourier transformation. Very obvious one, that you change the theory of NMR spectroscopy, provide a pulse, record a frequency FID, keep doing it, scanning, put them together, you improve the signal to noise ratio. The sensitivity problem was partly solved by using multi-scanning in pulse Fourier transformation, time saving, a number of other things also. So this was the story of NMR spectroscopy, that people start thinking of having techniques through which they can improve this. Okay. That was not the end of it. People thought that there should be some other ways of doing it. Number one, this observation that collapse of signal gives you a very intense peak, more than the collapse of signal is supposed to give, is something which one need to understand. So on one hand, people were trying to understand why this intensity enhancement takes place. Good sign. Sensitivity is increasing, but we don't know why. On the other hand, people were thinking that sensitivity of a signal is a pure population difference. Difference in population of two states. And this population difference between two states is dependent on hardware, which we don't want to change. Hardware, we want to be independent of hardware, because that was the money we could spend. 300 megahertz, the maximum money we could spend. We don't want to buy a 600 one, or there was nothing available after 300. So dependent on the applied magnetic field. They were also dependent on the gyromagnetic ratio, right? And we also know that population difference is signal, right? Proton has a population difference much larger than the carbon-13. Forget the abundance, the gyromagnetic ratio of proton and carbon is 1/4 of each other. Therefore, proton would have 4 times more population difference as compared to carbon. I want you to forget the gyromagnetic ratio. About natural abundance. I just want you to think over the difference in population assumed to be because of difference in gyromagnetic ratios. Proton NMR spectrum is sensitive because there is more population difference, right? And carbon-13 NMR spectrum is weak because there is a less of a population difference. We cannot increase the population difference because we don't want to buy new hardware. Okay? What we want to do something and that was the beginning of a fresh thinking. Can we do it differently? Proton is sensitive, carbon is insensitive, or proton is sensitive and nitrogen is insensitive. Both are coupled to each other. Proton gives 4 times larger signal as compared to carbon, forgetting the natural abundance, please, because this 6,000% less signals. But I don't want to take you into this dimension. Just forget that gyromagnetic ratio population difference is 1 into 4. So, proton signal is 4 times larger than the carbon signal, right? This is the basic fundamental simplified understanding. Okay. Proton is more sensitive because there is more population difference. And they both are coupled. So they share the energy levels. When they are coupled, they share the energy levels. Coupled is when there is a sharing of an energy levels also. We somehow transfer the population of proton to the carbon. So if I transfer the population or polarization of proton to the carbon, then the difference between one state and the other state increases, and I would have a increased intensity of a carbon. This was a fundamental, basic, theoretical understanding. No rationale. They didn't know how to do that. They didn't know how to manifest and practically carry out this particular experiment. And as I said, the theory in NMR spectroscopy is always developed first, then the experimental things came two-dimensional, except a few, like nuclear Overhauser effect. Overhauser effect was observed, and later people explained why Overhauser effect was there. So So the first property was that polarization transfer or a population transfer. I don't mind if you want to use word population transfer also. Can we use the bigger population difference from a sensitive nuclei from like proton and pass it to the less sensitive nuclei like carbon-13 and N15 all in a predictable manner? Remember, anima is predictability. If you can't predict, you don't know what you will get. In a predictable manner. Can we do that? Question was very, very simple. Can we use the bigger population difference of a sensitive nuclei and transfer it to the less sensitive nuclei, pass it to, loan it to less sensitive nuclei or insensitive nuclei in a predictable manner? There was a question. This was called polarization transfer. There were many names. There was selective population inversion, selective population transfer, polarization transfer. Eventually people agreed on a terminology called polarization transfer. And what technique is involved? Basically passing the large excess population of proton to the insensitive nuclei like carbon or nitrogen on which it is attached to. Remember, it can only happen when they are coupled to each other, because you are doing it through energy levels. How it can be developed into a practical experiment was a nightmare. People have worked extremely hard to make it happen. It's not like a money which I give it to you, you become suddenly poor. It's not the question of this. There is something which need to be done which selectively transfer the population of proton to the carbon. How it works, I would try to explain it to you in my best possible way. There are lots of different diagrams. I want to make you realize that when you have an uncoupled proton and carbon system, then there is no sharing of energy. There is no energy levels which are same. Carbon exists alpha and beta, and proton exists alpha and beta also, right? Actually, ulta, ye theek hai, sahi. Now, I would like you to see there is a problem in this diagram which I just seen. Although I see that this population difference, if you just forget everything else, the difference in two energy levels should be 1/4 to each other also, because this gyromagnetic ratio. So this ye fasla between this and this and this and this should be 1/4 of each other. But forget it. It's not so important. These are uncoupled system. What if you have a coupled system? If you have a CH, proton and a carbon, that is something which you need to understand. And believe me, if we don't go together, all of us, we would lose each other permanently. You understand what you mean by losing a person permanently? Right? So I don't want you to lose, I don't want to lose you all, I don't know how many of you want me to be with you and don't lose me. But anyway, let me just tell you what this means. This is a coupled proton-carbon system, CH. In the easiest term is a carbon-proton system. Always remember that every C13 which has a proton is coupled with that proton. Every proton is not necessarily coupled with C13, only 1%. Kal wali baat yaad rakhiye. Okay, so there are 4 energy states. If you combine them together, there are 4 energy states. One is, this is carbon spin and this is proton spin. Both of them are aligned to the applied magnetic field. right? So they are called alpha alpha, right? ये बोलते जाए मैं मतलब मजा नहीं आ रहा है. आपको पता नहीं कि शोरा को सबसे बड़ा मसला ये होता है कि जब तक उनको डांट ना मिले या उनको जबरदस्ती उतारा ना जाए वो खुश नहीं होते, राइट? ओके, तो बोल दें फिर. सो मुकर्रर ये है कि you have four energy state, very simple. One in, both of them are alpha alpha, both of them are beta beta. One of them is beta and the other is alpha, and this one is beta and alpha, right? Alpha and beta. Four energy state. Why this one and this one is not equivalent? Energy में equivalent क्यों नहीं है? Because of a simple fact that they are not proton proton or carbon carbon, they are proton carbon, and they have a difference in energy also. Now, if I want to record proton NMR spectrum and a carbon NMR spectrum together at the same time, the transition which you can observe is the following, and I don't want to confuse you. Carbon-13 1, this is the difference in the orientation of carbon-13, that this is carbon-13. हमेशा याद रखें जो right hand वाला है ना मेरा और आपका भी right hand वाला, ठीक है, is carbon. ये पता नहीं कहाँ चला गया. This is carbon, right? And this is proton. So carbon has a different orientation. They become alpha beta, right? No change in the orientation of proton. So the signal is of a carbon, right? In this case, you see the change in the orientation of proton. So this is a signal of, in this case, you see the orientation of carbon. So it is a carbon. And this between them is, so it is a proton. So it is a proton, these are proton transitions and these are carbon transition. There are four transitions. Two are proton transition in which proton spin is flipped, and two are carbon-13 transition in which carbon-13 is flipped. So there is and these two transition, the proton and the carbon and carbon, these two are absolutely equivalent, right? This is equivalent to this and this is equivalent to this. Okay? कौन अब तक मेरे साथ है और किसने दुनिया कौन है? सब साथ हैं? I can see some dead faces also. Yes, one dead body. Sorry. Sorry. Sorry, Fana. If you don't like, I can remove it. You don't like it. It just, I want to tell you that there are two different transitions. You know, among these four different energy states, there are two different transitions of proton. And if you want to distinguish them between them, is okay also. But what I'm going to do for this, I need to have this. I want to have this, right? Now, let's move forward. Exactly the same diagram. Now I want to say that both of them are spin half nuclei. दोनों spin half nuclei हैं, and they can exist as a plus half and a negative half. So you see these are plus half, right? Alpha states. Though both are plus half. Plus half carbon and plus half argon. And this is negative half argon, and in this you see the transition of only carbon. So carbon from plus become minus. And here you see a transition of proton into a negative. And here you see the transition of carbon into proton. Here you see the transition of proton from plus to minus. अभी तक खुश है? अब मसाइल शुरू होने वाले हैं. Okay, some of you would. Okay, forget it. Again, remember these are C13 transitions. These two are C13 transition and these are Ron transitions. And this 2 and 1 is just symbolizing two different transitions. 1 or 2, not different in energy. The energy difference between them is exactly identical, but the energy difference between this and this is huge, right? Okay, I want to give it a number on the basis of gyromagnetic ratio. I want to make it life much easier because मुझे ये प्लस हाफ और नेगेटिव हाफ को प्लस माइनस करने में ज़्यादा डिफिकल्टी होती है बचपन से. खैर, anyway, this is your gyromagnetic ratio proton and this is your carbon, right? Carbon 4 and 1, and I said that okay, this is plus, this is plus, this is plus, this is 0, this is plus. How many of you agree with me that this would be the situation when you would have like this? If I tell you that you kindly minus this from this, what would be the end result? Okay. And between this, क्या रह जाएगा? इसमें क्या रह जाएगा? कुछ भी नहीं रहेगा भाई. ब्रैकेट लगा के माइनस लगाना है, सही है बीच में. गॉड, इतनी मैथमेटिक्स तो मुझे भी आती है. Okay, so bracket lagane, and then you have to have a bracket and then you have to minus this thing also. When you do that, you would get this thing. You would get this and you would get this, जो आपने सही predict किया था. You would get this, ये भी आपने सही predict किया था. इसमें हम गड़बड़ कर गए थे, right? कोई शक, मगर इस शक का ताल्लुक एनवा से नहीं है. ठीक है? Try one. You want to try again? Bracket लगा के इसको इससे माइनस कर लें. What you would have? Right? ये कर ले, सारे लोग कर ले, इत्मीनान से कर ले. मुझे समझ में आ जाए तो मुझे भी बता दीजिए प्लीज. है ना? Do that. आज फिर बताएं. Okay. You see, this is a population difference which gives you a signal. So you do this and you would get this one. Okay? Here you have an absolute cancellation of carbon. Here you would have cancellation of both of them. You would have only... Now, if I place a population in terms of numbers को देना चाहता हूँ. I want to give them a number. And this number is 4 and 1 just based on gyromagnetic ratio. I don't want to consider the abundance right now at this point of time. How much is this one then? This one? This one, this one, difference between this and this one, difference between this and this and this and this. God, you're so intelligent. This is what it is. 5, 4, 0, 1. Difference between 5 and 4 is 1, right? and difference between 1 and 0 is 1. Difference between 5 and 1 is 4, and with difference between 4 and 0 is 4. So the proton signal would be 4 times higher than the carbon signal. Normal energy level diagram, forgetting the natural balance. Thank you so much. So the C13 signal is 1:1. Why doublet? Why doublet? Because it see the proton as alpha and beta, which you have seen it by yourself. And why proton also doublet? Now I want to do something strange. I want to change this population from here to here. I want to have a selective population inversion. I want to transfer polarization transfer from this state to this state. If I do that, what would be the case? I did it, and I put 4 from here to here and 0 from here to here. Now what is the difference? Now I want you to calculate the signal for me for proton. Proton, this is a proton transition, right? This is a proton transition, 5:1, 4, and this -4. So it would still appear as 4 times larger signal but inverted, one up and one down. On the other hand, the carbon has actually changed. 5 to 0 become +5, and 1 to 4 become -3. Do you see any enhancement of signal? This was 1:1. Remember this? Remember? Okay. Now you have a proton signal, which is again a doublet, but an inverted doublet, one up and one down in the same intensity. On the other hand, carbon intensity has actually increased 4-fold for a positive part of the doublet and increased 4-fold for the negative part of the doublet too. +1 to -3, 4-fold you wanna? Now, God, listen. Don't be confused. नहीं आया समझ में? Why people get angry also? Wait. ठीक है, सही है, जो भी है. Okay, this selective population transfer, I've done only one thing. I transfer the population of one energy level to the other energy level. Transfer, right? 4 go from here to here. Please don't ask me kaise hua hai, right? Don't ask me how it actually happened, because it's too premature that I tell you why it happens. But do you appreciate what actually has been done? That a part of the proton nuclei population has transferred from one population to the other population. And you were so happily calculating the intensities of proton and so happily calculating the intensities of carbon, and here you're so absolutely unhappy. This is again the same thing. Proton transition, these are the proton transition, here to here and here to here. Proton transition from 5 minus 1 is equal to 4, right? Between 0 minus 4 means -4. Proton signal was always 4. What has actually happened that one gone up and the other gone down, right? On the other hand, the real difference has taken place to the carbon signal, which was 1 only. And remember, you have lost your memory about the natural abundance. Please always remember. This is the reason why you're still so happy that you have one signal, although the signal intensity difference is 6,000 to 1. And I'll tell you why. But just remember that the original intensity of carbon signal was 1:1, doublet. 1:1 as compared to 4:4 in a doublet. When you have a selective population transfer, then you see a 1, 5 minus 0 is equal to plus 5, and 1 minus 4 means minus 3. You still get a doublet, inverted distorted doublet, because doublet is the one which has equal intensities. It's not the doublet in a true sense. On the other hand, 1 is plus 5 instead of plus 1, and the other is instead of plus 1 minus 3. So there is a fourfold increase in the intensity of the signal of carbon. Fourfold increase in the intensity of the signal of carbon. I don't know where is that slide. You agree with me? As a result of the polarization transfer, you see a plus half and a plus 5 and a negative 3. So you see a 4-time increase in the signal intensity, though, to be honest, this is a distorted signal, but visible more than it used to be before polarization transfer. Fourfold increase in the polarization transfer. So this is the technique called polarization transfer, and this, by using polarization transfer, you have seen by yourselves that you can increase the intensity of the carbon signal, which was 1:1 is now plus 5 minus 3. Remember, plus 5 minus 3 means 1:1 also. Increase minus करके देखे तो ही होता है ना. So I don't know why I'm confusing you. Just I want to tell you that plus 5 big signal and negative 3 big signal also distorted peaks, up and down. 4 times larger peak than the original carbon 13. And this has happened by a phenomena called polarization transfer, absolutely independent of hardware, by doing a manipulation called selective population transfer or selective population inversion for the proton. This is always a proton, right? Selective population inversion. ये होता कैसे है इसको अभी भूल जाए. I want you to again go through this with me. When you have a CH system, you have 4 energy levels. One is the one in which we have both alpha alpha, the other is beta beta, and the other is alpha beta and beta alpha, right? They are different from each other because they belong to different. This is the transition, this is the energy state in which you have a carbon-carbon bond spin flipping, right? The language. And this is the state in which you have a proton flipping, right? And this is the state in which you have a proton flipping also, and this is the state in which you have carbon flipping. And see, this has been deliberately made 4 times less than this, because the energy difference between the alpha and beta state of carbon is 4 times than the energy difference of proton. If you want to think separately, if you think separately, the energy difference between alpha and beta state of proton and carbon is 1:4, right? Proton, alpha and beta state has 4 times large del E as compared to carbon del E, right? So this is the reason why it made in a funny way that 2 states, alpha and beta, they are not equivalent, right? ये ध्यान में रखें कि this is the transition, and remember I made these arrows double headed, which primarily means that this actually happened all over, go up, down, every possible combination. The thing which never happened is from here to here. There is no allowed double spin transition. There is always a single spin transition. This is forbidden. ये forbidden है NMR में. And remember, forbidden is forbidden, right? This is forbidden. But chale, I don't want to confuse you. I just want to confuse you less. So you see that this is a transition of the carbon. It become alpha to beta, and this become, and in this case is a proton, in which proton become alpha to beta. And in this case you see a transition of carbon. In this case you see the transition of proton. Okay, easier. I just converted the whole thing into spin half, because we all understand that carbon 13 and proton and fluorine are spin half nuclei. So the spin half nuclei. And we all understand that plus half means a lower energy state, and we understand that negative half means, and here you have a plus half and a negative half, and you have a minus half and positive half. You minus this from this. You have a bracket in it, a minus sign, and you would get at the end of the day only proton, right? In this case you get nothing, because this is positive, positive, minus, minus. Minus into minus, and when you minus it, all of it, you get 0 here at the end. And then you do exactly the same thing here, exactly the same thing also. इसमें अगर किसी को प्रॉब्लम हो रही हो ना, तो रात को ठीक 11:30 पे, right at 11:30 you can start practicing. 12 बजे तक समझ जाएंगे. I'm telling you my own experience, right? Okay. Now this is plus C plus H. This is H, this is 0, this is carbon, and I just want to give them a number because number is easier to understand. So I said alpha, beta, gamma. Gamma क्या देना से? हैं? Gamma H is 4, the gamma C is 1, and therefore this population is 5, this population is 4, this population is 0, this population is 1, based on gyromagnetic ratio. And it's so simple because I know that the population of 5 minus 1 is a 4, difference of 4, because difference is the intensity. So a doublet which will appear, proton doublet which will appear because of the coupling with the carbon, will appear as a 4 and 4. And the doublet of a carbon which will appear because of its coupling with the proton is going to be 1 and a 1, and you can calculate that. This is the easiest thing which you can do. What I have done, what people have done, sorry, I didn't do anything. What people have done, they proposed a selective population inversion in one of the transition of proton. This is the reason why I put 2 and 1, right? This is the transition of proton, and this selective population inversion of population was carried out. 4 go here, 0 come here, and when it happened, you have a different population set. Up now this population is 0 and this population is 4. If you now want to calculate the intensity of a carbon signal and intensity of a proton signal, you come up with a different number. 5 minus 1 is 4, and 0 minus 4 is minus 4. this is carbon signal. 5 minus 0 is plus 5 and 1 minus 4 is minus 3. So the peak which will appearing as 1:1 for carbon and 4:4 for proton is now appearing as 4:-4 for proton and plus 5 and minus 3 for carbon. The peak which was literally so invisible, now I want you to bring your lost memory again. Natural balance. The peak which was so literally invisible is now becoming visible because you see a 4-fold increase in one part of the doublet and a 4-fold decrease in the other part of the doublet, but consequence is that you see plus 5 and minus 3 inverted two signals. Much larger signal as compared to this is called polarization transfer. And the name of this experiment is INEPT, insensitive nuclei enhancement by polarization transfer. I want you to write it. Acronyms are, I bet that I am one of those people who remember the maximum acronyms of NMR. INEPT, INEPT, insensitive nuclei enhancement by polarization transfer. Enhancement, again, the name says a lot. Enhancement of insensitive nuclei, which is carbon, by a process which is polarization transfer. And this polarization transfer has taken place from more sensitive nuclei to the less sensitive nuclei. Salman. Should not really confuse that carbon doesn't exist. I just want to give you a number of a population. This is a number given to the alpha beta states. Right? This is, as you see, that this is a real life situation in which we have a carbon which is only one fold as compared to 4-fold proton. So you see 4:4 doublet of a proton and 1:1 as a doublet of a carbon. This is just to make life easy, But when you, if I don't put a number, you would never be able to appreciate and comprehend the selective population inversion. Because that selective population inversion can only be calculated in terms of number in order for you to understand. When you have a 4 transfer to this and 0 transfer to this by a selective population inversion pulse. And I will tell you that in NMR spectroscopy everything is done by pulse. उसमें इरादे से ज़्यादा पल्स का दखल होता है, ठीक है? So when you do that, you have a situation like this. And when you have a situation like this, you have a 5 minus 0 plus 5. And I don't want to talk about this anymore because proton is not that favorite. What I have done right now is to show you, to demonstrate you that 1:1 small doublet is now become plus 5 and minus 3 distorted, inverse, right? One up, the other down. Doublet to hai BB. It's a doublet. But this has increased in size from 1 to 4 and decreased from 1 to minus 3. In both cases, there is an addition of 4 and a subtraction of 4. Net result एक ही है. But you see increased signals. And this increased signal is the blessing, because that's what you want to do. Is a hardware independent. You are able to you are able to see a much larger signal. I want to show you. This is coupled carbon CH, right? Doublet. Decoupled as singlet. Collapse of both of them together, maybe some NOE effect. In inept, this has increased, this one has increased +5, right? And this has decreased -3. You like this? You see a signal enhancement? Whether on a negative phase or a positive phase, if it is visible, it is enhancement. Isn't it? Right? That's what you want to have, You don't care whether it is a negative or a positive. A part of the doublet become negative, a part of the doublet become positive, but enhanced intensity. And that's what you want. So if you have the difference between this coupled and inept, you see a tremendous increase in sensitivity because of polarization transfer. Right? Because of a polarization transfer. And this technique is called inept, insensitive nuclei enhancement by polarization transfer. Then people said, good, nice, very, very nice that we can increase the intensity without improving the hardware by using a phenomenon called cross polarization or polarization transfer. They got this inverted peak, and some of them were not very happy with it, because you see, quartet would have 2 negative peaks, 1 positive peak, is all coupled, It's a bad thing actually. And a triplet would have 1, 0, the center peak would become 0, the one become negative, the other become positive, with much larger coupling constant also. They didn't like the inept. And they say that the inept is a distorted NMR spectrum. It's a distorted NMR spectrum, and when people start objecting on polarization, the results of a polarization transfer, then people said, of course we can do something. You see, we can fix it. And we can fix it by giving a delay that this negative signal doesn't really appear as a negative signal, but it appears as a positive signal, so it becomes a refocused inept. Exactly 3 years after the inept, a new experiment was introduced which called refocused inept, in which enhancement was there, but both part of the doublet were appearing on the same phase by just introducing a delay time. More of it was so-called refocused decoupled inept, because you see, a doublet is still appearing a doublet. It's still appearing as a doublet. And you don't like doublet, quartet, etc. Although they increase in intensity, but they still is a mushkil in your life, right? Nahin? All coupled. These are still coupled. This says refocus, decoupled, inept. Refocus, decoupled, inept. So these two together. Now compare the intensity of this signal and this signal. Intensity of this signal, decoupled signal, and inept decoupled signal. And this is because of what? Polarization transfer, right? Now you tell me, what is the use of it? You still don't have the multitude information about the multiplicity. And I tell you that you should not be worried about it. Once you're done with the polarization transfer, you add APT test in your experiment. And when you add APT test in your experiment, you would have methyl CHs appearing on one phase and CH2 appearing on, why not carbon, quaternary carbon? Doesn't have any proton. So therefore quaternary carbon, yeah, I'm so grateful, you're so kind. Thank you so much. Okay, so there is no polarization transfer. There is no polarization transfer in quaternary carbon. There is no proton, no polarization transfer. Therefore, quaternary carbon gone. the refocused, decoupled, inept with the ept would have quaternary carbon up. No, would not have any quaternary carbon, would have CH2 up and methyl and CHs down. Magic, nahi? You don't like it. समझ नहीं आ रहा क्या? You traveled all the way through. You traveled from a fully coupled carbon-13, right? Then you have done a broadband decoupling. You were not very happy with it because you lost the multiplicity, and at the same time the sensitivity was not that great also. You see, sensitivity is a problem. So sensitivity is an ever-present issue in carbon-13 NMR spectrum. And you did a polarization transfer. When you did a polarization transfer, you got a doublet, the same doublet. It has to be doublet, remember, because proton के साथ coupling के बगैर, without the coupling with the proton, you cannot transfer the population. You can never do that, right? So it become a distorted doublet of much more intense peak, right? And then lots of manipulation, introduce a delay. They were able to have a refocus pulse because refocus inept, and they said refocus inept is really very nice because you would be able to see a doublet as a positive peak, not as a negative peak also. Imagine inept of a cholesterol, in which you have half of the peaks of the same carbon down, up, down. This is even more complicated. When people said you increase the intensity, you made our life miserable. Because we don't even know, when they were all on one phase, at least we could make some sense. Now we don't know which part of the doublet is down, which part of the quartet is up, and it's just all nightmare. So they said, okay, refocus. People said, okay, intensity problem is solved. We are very happy with it, but we don't like it, because the so coupled, it's so complex. So we want to have a decoupled inept, and this is piece of cake. We decouple them, and they decouple after polarization transfer. So they have carried out a polarization transfer, decoupled it, and they got a refocus, decoupled inept, and compare this with this, and compare the intensity of this with this, right? And this intensity increase is because of the polarization transfer. This is polarization transfer. Question remain that, okay, we got a very intense peak of each carbon because of polarization transfer, but we lost the information about the multiplicity. And people said this problem is solved forever because somebody has brought an APT which can be built into every pulse sequence. Like you can build a spin echo in every pulse sequence. You do this experiment, again turn on the coupling, and then you let it happen like APT. Remember, so this is your situation after polarization transfer. After polarization transfer, before that you have a polarization transfer done. Right? Now in this polarization transfer experiment, you include APT test, which is just a delay, When you do that, you can distinguish between all three of them or four of them? Three of them, yes, three of them. Now if I tell you that I want to have quaternary carbon also, because quaternary carbons are carbons, so what do you do? So you would have a fully decoupled Cis13 and NMR spectrum, and you would just by subtracting it with the APT inept, right? And you would know which is quaternary carbon, which is CH3, which is CH2. You would probably still not know which one is CH3 and CH. You would still don't know actually. There is a problem, but चले for the time being कितना बुरा नहीं है. Now I would attempt to explain to you how it was done. This is the most difficult part, right? But I'm sure that you are so smart that you would understand that. Now, let me begin by asking you that if you want to play with both of them, how many radio frequency oscillator you need to have? 2? Okay. ठीक है? Okay. Now I want you to ये मैं अक्सर लोगों को बताता रहता हूँ. This is made by me. This is all made by me by using stencils, right? You know what is this? Huh? Nothing. You know what is this? What is this? Mistake है ये. And ये छप गई है, हाँ sir. अगर आपने की होती तो आपकी जिंदगी कितनी अजाब हुई होती है. Anyway, so हुआ ये कि I was trying to draw this magnetization vector from the down, and then I realized that इस सफ़े में इतनी जगह नहीं है, so I started from the up and I forget to remove it also. So इसको आप जब भूल जाइएगा, इसको आप ignore कर लीजिए. चलिए. Now I want you to this is your proton and this is your carbon, and you have two you have two different radio frequency oscillations, two pulses in two different nuclei at the same time. Okay, this is A, this is proton and this is carbon. नजर आ रहा है? नहीं? तो थोड़ा करीब आ जाए आप सारे लोग यहाँ, क्योंकि इसको तो पता नहीं क्या किया जाता है. I don't know what to do actually because क्या करें? Can you see this? ये arrow नजर आ रहे हैं? Can you see the arrows? And please, people from other location, can you see these pulse sequences and vector diagram?
Not clearly, sir.
Not clearly. Yeah. This is a problem. I'm really sorry. But do you have a printout of my presentation? You don't have a printout of my presentation also. Some of you would like to come closer to this. कर सकते हैं? Oh wow, shabash.
Again, but you have to scroll or use the.
हाँ, but I don't know कि मैं इसको ज़्यादा कैसे present कर सकता. Anyway, let me try. You have solved some problem. Okay. This is your proton pulses and this is your carbon pulses, and they all are going on at the same time frame. What you are detecting is क्या detect कर रहे हैं? You're detecting only the carbon, right? कह देना yes. What is this? ये क्या हुआ है? प्लस वाई पे आ गया ना? No एतराज? Okay, between them it is coupled with the carbon, so it must split into two parts. It has split it into two parts. One is slow moving and the other is fast moving. So they are moving apart from each other. सही है? And what is this? Always remember I told you that there is a 180x pulse. When you give a 180x pulse, what actually happens? But this 180x pulse, 180x pulse is not doing what I told you to do. Remember? This is a coupling, and I told you that the coupling never converge. Why it is converging? ये $1 zillion question है. This is $1 zillion question. Remember I told you that the coupling convergence cannot take place in a homonuclear system. When you give a 180H pulse, it doesn't really change the orientation of a coupled carbon because it is far beyond that, right? So what is actually happening that they are on the mirror image position and this is the H pulse, they continue to converge. But when you give a 180X pulse to the carbon, they start diverging. ये अगर आपने समझ लिया ना तो मुझे हैरत होगी, right? Okay. Start from there. 90 X pulse. This is the only thing which we know now actually. After that, we don't know. It's just all God's will. Huh? Okay. So this is A, right? And then it comes on coherent signal. Between this delay, it is split into two, obvious reason, because it is coupled with carbon. Proton की भाई proton तो देख ही रही है खातून. चले. So this is a CH system. So this is, one is moving slower and the other is moving forward. Here you are giving two 180 pulses. One is a 180 H pulse, 180 H pulse, and the other is 180 carbon pulse. Remember, this coupling is not because of the proton. This is because of the carbon, and it is an isolated system. This is a CH. Assume that this is CH has two quaternary carbon next to it, so don't forget it about any other proton contribution. When you give a 180 H pulse, they go to the mirror image position, but they are not relabeled. Remember yesterday I told you that when they relabel, the slower become faster and the faster become slower because of a simple fact that H pulse is not really doing anything to the carbon spin. H pulse is not strong enough to do anything with the carbon spin. So they continue to come together, it's almost reflexive. Right at that point of time, you have given a 180 X pulse to the carbon. When you give 180 X pulse to the carbon, the one which was labeled with the beta become labeled with the alpha, and the one which was labeled with the, now they would start diverging from each other, right? सारे लोग पानी पी रहे हैं. You know what is the best method of understanding it? Don't try. Okay, well I want you to try. Okay, just forget it. Right now you just forget everything. this continue to diverge. This continue to diverge until they become anti to each other on X, right? They're going away from each other, right? So they go up anti to each other. If at this point of time, if you give, I'm sorry, where we are gone. Oh my God, where we are now. Thank you so much. You take it, huh? God, where we were. And बस हो गया done. Okay. What I'm trying to do is to make us understand the consequences of different pulses together at the same time. This is the challenge, So, right now, you just remember, because I'll come back to it and I'll continue to talk about it until we all fell in sleep, right? Okay, anyway. So they start diverging from each other, and if you give a 90 vipers at that point of time, what will happen? इस पे अगर आप 90 vipers देते हैं, if you give a 90 vipers, what will happen? Yes? Okay. This is the spin inversion pulse, and I'll tell you what actually happened. But let's talk about carbon-13 also, because carbon-13 is playing a very important role. This is the carbon-13 which was here, right? And then you give a 180 X pulse, so it goes down, right? Right? It's not an XY plane. 180 X pulse goes down, right? Huh? 90 क्यों नहीं दिया? 90 इसलिए नहीं दिया कि we want to do something with it actually. We want to do something. Okay, this is a valid question, but I want to tell you that when you have a heteronuclear system, the pulses affect each other if they are of sufficient energy. Remember? So this the effect of 180 X pulse in carbon domain. You would understand it in few minutes. You would just hold on right now. So when you give now you remember this carbon-13 pulse sequence. Okay. When you give a 180 X pulse to the carbon, it comes to the negative Z, right? And then there is a delay in between. There is delay in between. This 190, this is 90 vipers. This is 90 vipers will bring this to where? Where it will bring it to? Where? It will bring it to XY plane, right? XY plane. And when you have this on XY plane, one is slower moving and the other is faster moving because of its coupling with the proton, right? And when you give a 90 vipers, there is a change of labeling and they would start diverging to one place, and then this is the one which you detect. Now, I want you to understand this thing. This is crucially important. Crucially important. This is minus 180. This is the 180 X pulse to carbon, right? And this 180 X pulse to carbon is this is a situation in which it is coupled with a proton. Coupling never go. They're coupled with the proton, although you don't see a splitting. The splitting would only come when they would be on XY plane. What you have done is the following. By giving a 90 vipers in H, which is a spin inversion pulse,